Welcome, PrepStation SSCE tutorial physics. Okay. All right, so lesson 1, we want to start with current electricity. Current electricity. The reason why we are starting with current electricity, we have two types of electricity, current electricity and static electricity. So in this lesson, we want to consider current electricity. All right. So these are the few topics we are going to consider: electric current, potential difference, electron flow, and resistance, factors that affect resistance, resistivity of a conductor, calculating resistance in a circuit, types of resistor, electrical power, and then galvanometer conversion. Okay, so let's start with electric current. Now, when electric charges are made to move or flow, an electric current is said to exist. Remember, I told you there are two types of electricity. One is called static, and the other one is called current. Now, in static electricity, the electrons don't flow. They don't move around. So they only gather and accumulate on a surface. Okay, but in current electricity, the electrons actually flow. So as the electrons flow, as they move from one point to another, it generates what is called electric current. Now, the size of the current depends on the number of coulombs of charge passing a given point. So that means the amount or the magnitude of current in a given circuit depends on how many coulombs of charge are subjected to pass through that particular conductor. So this is an example of what I'm talking about. This is a conductor, and here you have electrons. So as these electrons keep flowing through the conductor, current is generated. Okay? Now, the unit of current is the ampere. Often shortened as what? Amp. The symbol is A. Just like we have units of measurement in other quantities in physics. So the unit of current is ampere and is one of the fundamental quantities in physics. All right, so let's move further. Okay, so according to Coulomb's law, remember I told you that current electricity actually occur when charges are meant to flow, when they are forced or confined to flow in a conductor. So the formula you are looking at here is actually generated from the scientist called Coulomb's, Charles Coulomb's. Okay, and this was named after him as Coulomb's law. So according to this law, it defines current as the rate of flow of charge. The rate of flow of charge. That is to say, if the rate is high, then the magnitude of the current will be high. If the rate is low, the magnitude of current will also be low. And mathematically, we can express Coulomb's law as this, that I is equal to Q over T, where I stands for what? Q stands for the charge measured in coulombs with respect to the scientist called Charles Coulomb. And then I is the current measured in amperes. I already told you before now. And then T is the time measured in seconds. So that means if the timer is given in hour or minutes, you have to convert it to seconds because the SI unit for time is seconds. So I equals to Q over T. Now, let's look at potential difference. I've just talked about current. Now, what is potential difference? Actually, in electricity, these are the parameters used in defining or explaining electricity. That is current and voltage, also known as potential difference. Now, for a current to flow around a circuit, a driving force is needed. Yes, if we go back to what is called the Newtonian physics, according to Newton's first law, which is also known as the inertia law, it says an object will continue to be at rest until what happened? Until a force is applied to make it move. So the same applies to electric circuit. The electrons or the charge will not just move on their own to generate current. Something has to move the charge according to Newton's law. Okay, so the driving force is the difference in voltage between the start and the end of the circuit. So voltage is actually responsible for the driving of electrons through a circuit so that current can be generated. Now, the larger the current you want, the greater what? The potential difference that is required. Now, potential difference is best understood using the water analogy as shown below. There are other examples, but I like using the setup of water to explain what is potential difference. So let's look at the next slide to understand that better. Now, what we have here, of course, this is a dam, okay? This is a dam, and then you have the dam water falling through, and then through a tap, okay? So what happened here is, because the water is coming from a very high point, the pressure of the water drop will actually be very high. Now, the high pressure in water drop, just like what you have in your homes in plumbing work. If the storage tank is high up there, the pressure of water moving around the building will be high. That is what is happening here. So if the pressure is high, that will give more current flow of water. So this is also applicable to electric circuit. If the potential difference is high, more current will be delivered. More current will be delivered. Now, a short drop between storage and tap gives low. Now, water pressure, a low PD. Output from the tap, low current. So if the pressure from the water, as you can see, is low, then it will produce what? Low current. If the pressure is high, then it will produce high current. Now, how does this apply to electric circuit? Let's move forward. Okay. So also a large drop between the storage and the tap gives high water pressure. Okay, I've explained that. So when it's low, you have low pressure. When it's high, you have high pressure. And that is what plays out here. So let's continue and see how we can use this to explain what happened in electric circuit. Now, what you have here is a typical electric circuit. This is a battery, also known as cell, depending on how you are looking at it. Now, the difference between cell and battery. A cell is a device that converts chemical energy to electrical energy. But battery is an arrangement of cell in series. So if you have cell arranged more than 1, 2, 3, you call it battery in physics explanation. Now, this is a cell providing the potential difference. And then the arrow signifies the movement of charges around the circuit. Now, strictly, potential difference is defined as a measure of the energy given to the charge carriers. I told you before, the charges, the electrons will not move on their own. Something will have to move the electron. So the work of the cell or the work of the battery, in a layman understanding, is what? Is the source or the driving force of electrons in a circuit. Now, the charge carriers in an electric circuit obtain their energy from a power source or power supply called cell or battery. I've explained the difference between cell or battery. So without the cell or the battery, the electrons will not move around the circuit. And if electrons cannot move around the circuit, current cannot be generated. All right. An external wire connected to a battery will have electrons flowing through it as shown. That is what this diagram represents. This is a battery. This is an external wire. This extension is only trying to show that right inside the battery, the circuit continues. The circuit does not just stop here. So the electrons drop from this point. This is called a conventional current flow. Electrons flow from the cathode, that is the negative terminals of the battery, and then in turn, current is generated from the positive, which is called conventional current. Now, in completing the circuit inside the battery, the electrons need to flow from the positive to the negative terminal. They will not do this willingly, so they have to be forced through the battery. Yes, they will not do this willingly. They have to be forced through the battery so that current can be generated. I want to believe you got that, so let's move forward to something else. Now, electricity is the flow of electrons in a wire. Yes, we have established that fact, and I've shown you this diagram before, but we are going to something else. Now, all materials exhibit some opposition to current flowing through them. Yeah, all materials, even if you call it a conductor, they have a little element of opposition to the flow of current. Yes, they do. I will explain that shortly. Okay? Now, all materials fall into one of these three categories as far as their electrical conductivity is concerned. So when it comes to electrical conductivity, materials are grouped into three. We have what is called the conductors, we have semiconductors in between, and then we have the insulators at the extreme end. Now, I said each of these, they have an amount of opposition to the flow of current. So let's quickly look at that in details as well. Okay, now conductors, what do? Conductors show just a small amount of opposition. You may not get this now, but if by the time we're looking at alternating currents, okay, you get to understand that even a conductor has a level of what? Opposition to the flow of current. So conductor, why they are called conductor is because they show small amount of opposition. It's not as if they completely allow electrons to pass. No, just a small amount of opposition. And then semiconductors, of course, they stand in between. You can find these conductors on the periodic table, that is in the transition element. They actually come from what is called the metalloids. They are in between the metals and the non-metals. An example is silicon and germanium used in producing semiconductors. Now, this material or this category show medium to high opposition. Okay, they are semi. Semi means half. So they are partly insulator and partly conductor. Are you getting it now? Now, number three is insulators. Show very high and extreme opposition. Okay, these sets, they show very high and extreme opposition to the flow of current. All right. So with this in mind, what is resistance? What is resistance? So this opposition is called electrical resistance. So resistance is a measure of how much a material tries to stop electricity passing through it. That is what is called resistance. And every material has some level of opposition to the flow of current, as we're going to see shortly. Okay. Now, the amount of resistance depends on a number of factors. I have 4 here. Okay. Sometimes you see 3 in some textbooks, but I'll give you 4, and I will explain why we have 4. Number 1 is the length of the material. The longer the length of the material, the higher the resistance. Just like you have in plumbing network. The longer the pipe, okay, the lower the currents flowing. Lower current means higher resistance, okay? Now, the cross-sectional area of the material, the nature of the material measured by what? Resistivity, and then finally, the temperature. So resistance in a circuit are affected by 4 factors. Take note of that. Number 1 is the length of the material. Number 2, the cross-sectional area. Number 3, the nature of the material. And then lastly, temperature. Now, how does this affect what we are talking about? Factors that affect resistance. Number 1, length. The longer a wire is, the higher its resistance. Remember, resistance is the opposition to the flow of current. So if resistance is increasing, it means current is what? Decreasing. It's an inverse relationship. When electrons travel down a long wire, they can collide with more metal ions than a short wire. That's true. So if the length is longer than what is supposed to be, it takes time before the electrons could get to the end. So they collide with the ions of the metal, thereby reducing the flow. All right, so the second factor we want to look at is the cross-sectional area. Now, a thin wire has a higher resistance than a wide area of wire. Now, let me use this diagram to explain that. Just like in your normal water plumbing network at home, bigger pipe, for example, let's say 4 cm pipe, cannot produce the same amount of water as 2 cm because of what? The cross-sectional area. This will produce more current or more amount of water than this. And that is exactly what happened with the electrical circuit. So wire with much diameter, larger cross-sectional area, produces more currents, okay? And of course, you know, more current means decrease in resistance. Then wire with smaller cross-sectional area produce what? Smaller amounts of current because the resistance is high. And that is why even at home electrical installation, we check the size of wire used for electrical connection. For example, you cannot use 1 mm or 2.5 mm for connection of air condition. Use something like from 4 mm because the device, the amount of current consumed by the device also depends on what? The wire to be used. So a thin area wire has a higher resistance than a wide area wire. So let's continue. Now, wire 1 and wire 2 are made from the same material. This symbol rho is called resistivity. It's the same for both wires and the same length. L is also the same, okay? Wire 1 has twice the cross-sectional area of wire 2. What does that imply? It means wire 1 has half the resistance of wire 2. This is wire 1. So it has half the resistance, which implies that more current will flow compared to this. Does that make sense? So that is factor number 2. Let's quickly look at factor number 3, material. Yeah, material. Now, remember when we started, I gave you 3 categories of material when it comes to electrical conductivity. Remember, let me mention them again. Conductor, semiconductor, and insulator. So depending on the nature of the material, it also affects resistance. Different materials have different resistance because some materials are better conductors. Okay? Now, nichrome wire has a higher resistance than a copper wire of the same size. This explains why copper wire is the best when it comes to electrical conductivity. Okay, because it has a lower resistance compared to nichrome wire. All right, and then lastly, temperature. Now, the higher the temperature of a wire, the higher its resistance. That's true. This also applies to Ohm's law. Remember, we are getting there. Now, metal ions vibrate more at higher temperature, and so collisions with electrons are more likely to happen. Let me say that again. Metal ions vibrate more. And of course, this is linking us back to what is called a kinetic molecular theory of matter, which has to do with what? With heat. Okay? So when you heat a metal, what happens? The metal ions gain what is called kinetic energy by virtue of motion. And as they begin to move in random motion, colliding with one another, colliding with other ions, colliding with the walls of the container, for example, liquid, they increase what is called pressure. All right? So temperature increases the vibration level of ions. So when ions, the vibration level increases, it causes more collision to the electrons, and that is resistance as well. So these are the 4 factors. Now let's move to something else which I mentioned in the course of explaining the 4 factors that affect conductivity, and that is resistivity. Every material has what is called resistivity. Resistivity is the opposite of conductivity. So even when we refer to insulators, insulators have high level. Every material have what? Different amount of resistance, just like we have conductors. Different conductors have different amounts of conductivity. Now, the resistivity of a conductor depends also on some factors, okay, which I'm going to mention quickly. Now, it's directly proportional to the length, the resistivity. Remember the 4 factors I mentioned. When I was explaining length, I said the longer the length, the more the resistance. Now, what is the relationship there? It means resistance is directly proportional to the length of the conductor. In other words, increase in the length of conductor, increase in resistance. So that is what we have here, a direct relationship. And then inversely proportional to the cross-sectional area of the conductor. What does that mean? Now, what that simply means is increase in the diameter of the wire, increase in the cross-sectional area, simply means more current will be delivered. And if more current is delivered, it means the resistance is low. Okay? So that means the relationship here is an inverse proportion. Increase in one, decrease in the other. So if you put this together, then you have this. What I have here is a joint variation. It's actually derivation from 2 of these. So the first statement says R is directly proportional to length. The second statement says R is inversely proportional to area. This is a direct relationship. This is an inverse relationship. So if you put this together, you have what is called a joint relationship. And of course, in mathematics, to remove the proportionality sign and introduce equality sign, you must introduce a constant. So that constant is what we have here. This constant is called rho, and rho signifies what? Resistivity. So every material has some level of what? Resistivity. In other words, we are saying amount of how much they can resist the flow of electrons through them. Okay, so let's move forward from here. Okay, I've already explained that mathematically. Okay, so where R is resistivity, I'm explaining the formula now. Measured in what? R is resistance, so I mean measured in ohms. This is the symbol for ohms. Then rho is resistivity measured in ohm meters. Then length measured in meters, of course we know that. Then area measured in meter squared. All right, let's move forward from here.